So in the previous lesson, I stressed how realistically, most likely, we don't have data from an entire population. So therefore, we wouldn't be able to calculate the value, let's say, of a population mean mu or a population proportion p. So what we've been saying is that rather than getting information from the entire population, we take a sample and we could use sample information to estimate these certain parameters from the population. Specifically, we use X bar as an estimate of mu, and we use p hat as an estimate of p. So realistically, in practice, we only select one sample to compute a point estimate. However, what you have to realize is that the sample that we select is only one of the many possible samples that could have been selected from the population. And samples do vary. So one major disadvantage of using one sample mean as a point estimate of the population mean, so using just one value of X bar, let's say, as an estimate of mu, is that we don't know how close or far the point estimate is from the true population mean. So whenever we're using a point estimate to estimate a population parameter, we're not sure of the extent of the error involved in the estimate. So remember, there's always sampling error, and we talked about that in chapter 8. So when we use one value to estimate the true value of something, we don't know how close or far the estimate is. So in other words, is it a good estimate? So this is really, really important to understand. I'm going to highlight it. So one major disadvantage of using one sample mean as a point estimate of the population mean is that we don't know how close or far the point estimate is from the true population mean. So what we do instead is we get an interval estimate. Now, an interval estimate is a range of values within which the population parameter is likely to fall. So rather than just using one number, one point estimate to estimate the population mean, let's say, we're going to get a range of values. So that's more likely to contain, this unknown parameter. So this technique uses a point estimate, but along with the associated sampling error to construct this interval to estimate a population parameter. And that's really where we're going in this chapter. So we're going to construct what's called these confidence intervals for the population mean and the population proportion. They're very similar in terms of the formulas, except they're two different parameters, right? One, we're trying to estimate the mean, mu. The other one, we're trying to estimate P, the population proportion. So we're going to start in 9.4 estimating the population mean using a confidence interval. So we said in comparison to a point estimate, which uses a single value to estimate the population parameter and is very unlikely to be exactly equal to the population parameter, an interval estimate is going to use a range of values to estimate the population parameter. But we need to use probability. A probability level can be assigned to the interval estimate, which is going to indicate how confident we are that the interval will include the value of the population parameter. The probability level that's associated with an interval estimate is called the confidence level. So we're going to be, and that's why we call it a confidence interval. So along with the point estimate and the sampling error, we're going to use a certain level of probability. That's going to let us know how likely, it is that this parameter that we're trying to estimate is going to fall within that range of values. So this type of interval estimate is called a confidence interval. So I'm just going to write down that we use C. That's what C is going to be, the confidence level. And every time we construct a confidence interval, we're going to have this C level, this confidence level. So we're just going to call it C. So like I said, first, I'm going to show you how to construct a confidence interval for the mean. But we're going to assume that the population standard deviation is unknown. So because if we don't have information from the entire population, right, and we can't calculate mu, but we're trying to estimate it, then how are we going to know sigma? Because we need mu in order to calculate sigma. So most likely the population standard deviation sigma is also unknown. So then we need something to estimate sigma, right? And sigma stands for the population standard deviation. So what we could do is we could take our sample and get the sample standard deviation. So we could use S, the sample standard deviation, as an estimate of sigma. And I actually have that in the second bullet here, so we'll get there in a minute. But like I just said, in most real life applications, the population standard deviation sigma is unknown. So a more realistic approach to constructing an interval estimate for mu, the population mean, is to consider the situation where the population standard deviation is also unknown. So if we don't know one, we probably don't know the other. But what we could do is we can use, so whenever sigma is unknown, we can use S, the sample standard deviation, as an estimate. But when that's the case, z-scores can no longer be used to construct a confidence interval for a population mean when we don't know the population standard deviation. So in chapter 7, when we were using the normal distribution, we were assuming that we knew sigma, right? Mu and sigma. So now we can't make that assumption because we're sampling, we're using sample information, as an estimate. So this mathematician, W.S. Gossett, discovered that when we use S, the sample standard deviation, to approximate sigma, the population standard deviation, and we substitute, S in for sigma into the Z formula, this new statistic was not normally distributed. So he called this new statistic a T statistic, or a student's T distribution. It looked similar to the normal distribution. It was bell-shaped, symmetric, except it was more varied. So that's the key with the T distribution. It's flatter and wider than a normal distribution. Even though it looks normal, there's just more variability. So I just want to recap, and then this would be our formula for T instead of Z. We're no longer using Z right now. So remember, let me just remind you in chapter 3. Actually, I'm going to open Word. Hold on 1 second. I'm going to get the whiteboard. So I just want to go back and remind you that Z is equal to the data value X minus the mean of the population over the standard deviation, right? This is assuming, we have information from the entire population. But when we're using, before I point that out, let me just say, so this is when we're using the for the random variable X. So X is our random variable. Now remember in chapter 8, X bar was my random variable, right? When we were looking at the sampling distribution of the mean. So let's say X bar is my random variable. Then I would have to subtract the mean of the distribution, which is the mean of all the X bars, right? And then I would have to divide by the standard deviation of all the X bars. So this is when X bar is our random variable. But in either one of these cases, we were assuming we knew sigma, right? But when sigma is unknown, we use S instead, which is the sample standard deviation. So my Z-score would look like this. We would take our sample mean minus mu sub X bar, right? The mean of all the sample means. But now we're using S as an estimate instead. So S sub X bar. This is not a normal statistic. We call this a T statistic. So we're going to use T instead whenever we're using S as an estimate of sigma. So S sub X bar is just equal to S over the square root of N. Because remember, sigma sub X bar, I'll put this over here. Change this to red. Remember, sigma sub X bar is equal to sigma divided by the square root of n, but I'm replacing sigma with S now. And we have a t statistic. So we do have, so let me go back to the worksheet. This t value now, and we also have a t table for the t distribution. So the conditions, let me just wrap up what I just said. So the conditions in order to use the t distribution, in order to construct a confidence interval for the mean, is that the population standard deviation sigma is unknown, and we're going to estimate it using S, the sample standard deviation. And we're still assuming the population from which we sample is approximately normal. So when we use the t distribution and we look up on the t table, which I'm going to do in the next lesson when we actually construct a confidence interval, we're going to look up what's called degrees of freedom. Degrees of freedom of a statistic are the number of free choices used in computing the statistic. We denote degrees of freedom by df, and they're equal to the sample size minus 1, so n minus 1. Now, I don't expect you to fully understand degrees of freedom. It's a hard concept to understand. In an introductory course like this, all I want you to know is that when we go to use the t table, and I'm going to show you this in the next lecture, you're going to look up degrees of freedom, which is always sample size minus 1. And before we wrap up this lecture, let me just go over the properties of a t distribution. I'll show you what it looks like in the next video. So like I said, the t distribution is bell-shaped. It's symmetric about the center, t equals 0, just like a normal distribution is centered around z equals 0. But the t distribution is more varied and flatter than the standard normal. And the variability of the t distribution depends on sample size. So for every particular t distribution, we're going to calculate degrees of freedom, which is n minus 1. And as sample size increases, anyway, remember what I told you back in chapter 8, according to the central limit theorem, X bar is going to follow an approximately normal distribution anyway. So as n gets sufficiently large, the t distribution would look approximately normal anyway. So in the next lesson, I'm going to take everything that I just lectured about in this lesson, and we're going to do an example.